Hello, everyone. Welcome. My name is Stuart Schaefer. I'm an architect at Microsoft, and I'm working on bringing AI and ML into the Windows platform. I'm here with Daniel Kennett from the Xbox ATG group and Yuri Uralski from NVIDIA to talk about work that we're doing to really work on bringing machine learning into gaming. There we go. So today what I want to run through quickly is how many of you here have heard of Windows ML, lots of press and lots of great stuff about it. We'll go through really what the foundation of Windows ML are, a little bit about the API, some of the work that we're doing with partners like Unity, and really sort of talk about what we're doing with it in gaming and what we see coming up ahead. In general, when we look at machine learning, we brought it into Windows for a couple reasons. What we see a lot of is that there are an incredible number of applications for machine learning that are just becoming incredibly practical and realistic to use. In gaming, we see things like denoising and superscaling, animating characters, scene generation, NPC AIs, lots of techniques that are starting to mature based on machine learning. And those are things that are really important scenarios to our game developers that we really want to make first class in the platform. So for us, what we're really trying to accomplish as Microsoft is to make machine learning a first-class part of the hardware to allow you to get access to all of the silicon that's underneath. There's a lot of revolution happening in the hardware, and we want to make that something which is first-class part of the system, really able to extract all that benefit for a game developer and target every possible bit of hardware that you can, all the silicon that's possible in the game that you have. What we're going to do today is really kind of give you an overview of Windows machine learning. There's a second talk after this over in room 3022, which will really go deeply into performance. So Windows machine learning is really designed to work on the breadth of hardware, and we're going to also talk deeply about how we get performance, and that's the next talk. So really where I want to start from here is, I don't know how many of you yesterday got to see this. Let's see. So yesterday, the folks from Seed did a demo that showed how to do AI and ray tracing together. And really what we saw was kind of interesting was, the application of really advanced graphics hardware and graphics techniques, but also machine learning mixed together in the game. Self-learning agents that played and learned alongside of the AI, or alongside of the advanced ray tracing. So for us, when we take a look at this is a really good example of what we see happening in games in the future, is really the fusion of two really state-of-the-art technologies to make really advanced games. Awesome. I really love the little robots kind of interacting with each other. One of the things that's really important that we sort of think about machine learning and AI is that it's technologies and techniques that have been around for quite some time, but really scale has changed everything and made it possible. What we've seen in the deep learning space is that really what we've come to is a place where we can use neural net technology to be as accurate as human beings at things that we consider human level skills. Hearing and seeing and input, all the types of things that we think of as human cognitive skills have really become accurate enough to be state of the art. And those things are driven a lot by the fact that we are really good at collecting very large data sets. Deep learning networks are really hungry and require millions and millions of labeled rows to really understand what's going on inside of things. We also have an incredible amount of computing power, and the synthesis of those together has really driven our ability to do things that human beings can. That, plus when we really look at one thing that has driven us to the place that says, awesome, now we have these great skills, are they really ready to use? To be honest, they are. We really have seen a lot of maturity in the tools and framework space. We've seen the ability for us to really increase the accuracy of these networks while also increasing the efficiency of the hardware that's underneath. We've also seen something that's really important is that the algorithms themselves have gotten more efficient, as I said, sort of leverage the operations that are possible underneath the machines and reuse some of those same technology across multiple domains. One of the things that's interesting about vision that we don't think of is that us as human beings, we can recognize many, many different things. But often when you train a neural network, it's very, very good at recognizing chickens or cows or something very specific. But we've learned how to reuse all that information and reuse that core skill and apply that to many, many different places. So those things have really given us a lot of tools in our toolbox to make machine learning something which is both usable and useful itself. So as I mentioned before, my job is to take AI into Windows. And there's a number of driving reasons that we really want to bring AI into the core platform. One is that what we see is really important is that machine learning is important, but it really requires very low latency, real-time results for you to drive the use of the technology in the game. There's a lot of things about computer vision that are very interesting, but if it doesn't keep up with the pace of the game, it really is not useful. So we really are driving hard to make sure that we can make performance one of the core things that we do in the Windows platform itself. We also want to make sure that you have the ability to really look at two things: flexibility and operational costs. You can run machine learning on the CPU. You can run machine learning on a GPU. You can run it in the cloud. You can use all the techniques and all the locations possible to run the machine learning workloads that you may want to run now and in the future. So using that sort of core driving sort of factor, what we did is we built what we call Windows ML, or Windows Machine Learning. The basic idea behind Windows Machine Learning is I want to build an application. If I want to build an application that uses machine learning, the first thing I actually really need to do is understand what is the problem I'm trying to solve, and then how do I build a model to do that. And I'll go up to some form of training framework in the cloud or on a desktop, design that model, gather a whole lot of data, and train that model. Once I've trained that model, I take that model file and I can now add it to Visual Studio using the normal things that we think of in Visual Studio and add a model reference to my project. It will synthesize code, help me use the platform that's underneath, and run that on top of Windows Machine Learning. The core idea behind machine learning is to really simplify the use of the model itself and the use of the underlying technology, so all the hardware in the system can get abstracted. And what we have is a process that we call load, bind, eval. First, you load the model into the Windows Machine Learning runtime, and it will basically analyze that model and decide how to run that model. Then what you do is you connect together the inputs and outputs. So if I want to do a computer vision operation, I can connect a camera or a photo or something from the DX pipeline to the model itself, perform my operation, and sort of be able to put out the output results in the same way. I take those bindings and then I provide it to the engine, evaluate that model, and I get the results of my evaluation. That core pattern drives behind what we do: load, bind, eval. I'll show you a lot more of that later, but that's the real core flow of Windows Machine Learning. Windows ML architecturally sort of follows three basic layers. At the top layer are a set of APIs. Those APIs exist as core Win32 APIs. I'll show you a lot about that later. They're very similar to what you're used to in working with graphics. On top of that, there is a set of further application APIs that allow you to use them in a UWP application across the breadth of our technology at Microsoft. So you can run it in the store, you can run it on a desktop, you can run it anywhere. And the core goal is that Windows ML will show up in every Windows edition throughout this year. So what we have today is it will ship in desktop, and throughout the year, it'll keep filtering into all the editions that we have. Also, at the upper layers of the system, we've spent a lot of time to make sure that not only do we work with games, we work with a lot of the hardware that's on the machine. So if you're doing, as I mentioned before, computer vision, which will go throughout my talk, we spent a lot of time to make sure that the hardware pipeline for images and camera are things that are connected together deeply with the rest of what we do. So making something efficient that comes from the camera into the game through the DX pipeline is something you'll see as a theme throughout all we do in Windows ML. Underneath that, when you actually have loaded the model into the system, there is a runtime that allows us to basically do the inferencing or decide how to use the model and get the outputs that we're looking for. That inference engine manages the model and manages the resources required to basically run that model. So a machine learning model is a lot of math, and there's a lot of allocation of memory and usage of resources. As you'll see, it's a quite hungry beast. And in doing that, the engine really designed to require how to pull together all the allocations necessary to make sure that it's performant as well as doesn't take your machine down. So it loads together and compiles all the pieces that are necessary to run the operators that drive what's called a data flow graph, and I'll show you a little bit more about that later, and really execute that graph against the hardware. Underneath that, we have a layer that's really driven basically on abstracting away the hardware and device itself. We've built a technology that we call DirectML. That technology is really designed to leverage the DX pipeline and run on any GPU that exists, as well as upcoming neural network hardware. If you've seen other things that we've done, we've shown this running on NPUs and other hardware from other vendors. So in general, what happens is the core of DirectML generates shaders, and those shaders can get projected onto any underlying graphics hardware. We've also done a lot of optimizations on the CPU so that you get the best out of the CPU and optimized every class of CPU instruction that we've seen, from SSE all the way up to AVX 512. But as I mentioned before, I'll remind you again, if you really want to see how we get performance, we have another talk after this that will show you deeply how DirectML gets deep performance on the hardware that we have. So Windows machine learning really is driven by the core, as I said, the loading of a model into the system. Where do we get models from? Well, we took a very hard bet on something we call ONNX, the Open Neural Network Exchange. We use those models natively in our system. So when you create a model in any framework that exists today, you can take that model and import it into an ONNX model. We teamed up with Facebook and Amazon and have joined together with a lot of other companies, Intel, NVIDIA, Qualcomm, and others, to be able to sort of really drive a standard format for us to build models and evaluate them in systems. So we use that ONNX model natively. We have built a whole body of tools we call WinML tools. We've given a lot of those back to the open source and put them up in the ONNX consortium. So they are free, public, open domain, conversion utilities. We support today a lot of the major frameworks, Caffe2, CNTK, CoreML, SparkML, all different kinds of machine learning libraries where you can build and train a model and then import it into our system using ONNX. You can also use cloud services. So you can use Azure Machine Learning, build a model in Azure Machine Learning and export it. And coming soon, the Azure Custom Vision service will allow you to basically just take data, provide it to them. Here's the photos of what I'd like to analyze, and they'll produce a model directly in the ONNX format for you. So using that ONNX model, the thing that really drives the heart of the system, from there, what we can do is bring that into our system. So if we want to think about what to do with that model, a lot of it comes down to what's the technique or the thing that I'm trying to accomplish. In computer vision, the most sort of basic 101 thing that we do is handwriting recognition. There's a common data set called MNIST, which is about 60,000 or so handwritten numbers and letters, or actually it's numbers. And really what we've done is a simple model to basically look at how do you analyze something like handwriting. In neural nets, a lot of what's become state-of-the-art in computer vision is not just taking a look at something and classifying it, but try to understand what it is. Behind the scenes, what a convolutional neural network does for image processing is basically takes a look at an image and runs a lot of processing that we're used to seeing in graphics. So a convolution is really taking a filter and applying that filter to an image to extract out what are features. So if you look at, so here the number 8, what we'd look at is try to find in an early layer all of the different edges. So what are the places that there are color differences that I can define what those edges might be in the system. And then once I have those edges, how do I define corners? How do I define all the individual features of the image so that as I go through all the stages of the neural network, I can put together further and more successive features. So we use a sort of combination of techniques, first convolution to extract features. And then once we've extracted features, we use operators like pooling, which basically selects regions on the screen, regions in the image to really define how do we have a way to denoise that and create invariance spatially. So if you think about when I'm drawing a number 7, there's a straight line at the top and then a number 7 and a slash. But if I happen to draw it this way, I don't want my neural network to basically think that that's a different thing. So by doing these techniques, what it really allows us to do is become invariant to some of those differences. The combination of all those together really is what allows me to put together a whole set of macro features and then classify the end result. So what we're going to do here is take a look at what is image recognition in a convolutional network. And I'm going to try and walk through what that would look like a little bit in code and then show you a demo of that. So when we look at this network, it's called MNIST. What we would be doing with Windows machine learning is really starting off with, okay, I've built that model. How do I bring it up in my system? On the right-hand side, what you'll see is there's a tool I'll talk about later called Netron, which is a visualizer of your model. You can see what the inputs and outputs of that model look like. If you load the model up into the runtime, we have a set of commands that exist to view the metadata of the model itself. So you think about those bindings that you have to create that says, here's my input, it's an image, what's the format of the image? The format of the image in the case that's shown up here on the screen, if you can see it, you can see that it basically tells you how many channels of color that are required. This is grayscale in MNIST, and how many pixels it's expecting. So those things really define the shape of the inputs and outputs once I've loaded in the system. But in general, the way it works in Windows ML is basically you'll start up and create a runtime. That runtime is an instance of the inference engine underneath it. Once you've created that, you'll load the model into the runtime. The model will get analyzed by the runtime to see what those inputs and outputs look like and be able to provide you that core metadata. So after you've loaded that up into the system, now you're ready to decide, okay, what am I going to do with that? The next thing I typically do is I will bind the resources of my application to that. In the case of what we do here, so we support in Windows ML things which are CPU-based resources and things which are D3D-based resources. So you can use things from your gaming pipeline and bind them to the inputs of Windows machine learning. So in the most basic case, what you start off with is you select which D3D device you want to run on. So if your system has multiple GPUs, you can choose which GPU you'd like to run inferencing on. It also turns out that if you pass in null, what you'll get is the CPU. So you'll get a null device, and just so you know, it's not warp. We don't use warp to do anything. Basically, we use the CPU as the machine learning version of warp. So what you'll do is basically choose the device you want to use for inferencing and then bind your resources. Every resource, like in D3D, you'll create a descriptor that defines to the system what this thing looks like. So what's its shape and dimension, what are the data types that are contained inside of it, and then a reference to the image itself. So basically in this case here, we have a tensor. A tensor is a fancy name for an n-dimensional matrix. That matrix really contains what that image is. So if you think about a RGB color, it's 3 channels, right? So 3 by whatever the size of my thing is. In the case of MNIST, we said it's grayscale, so it would be a 1-dimensional by however big my pixel is. So we define that we have a tensor. The tensor contains floating point data, which is float 32. There are 4 dimensions here. I mentioned 3, but if you look here on this thing here, it says 1, 3, 25, 25. 1 is a batch dimension. So we always do what we call NCHW. N is the number of images we want to run at the same time. So that's the batch. Here we'll do a batch size of 1. 3 is the number of channels we want to use, and then 25 by 25 pixels. So we can take that, put that into the system, connect it up together. As I mentioned before, our goal is to support D3D resources. In the current version that exists out in the public today, we only support UAV textures, UAV resources. We will continue to sort of, as we go through the development, support much more than that, but today you'll see that we support UAV. On top of that, what's really important for us is that it is an asynchronous process. What I'm showing you here is that there's no restriction for you to create n bindings. So if you want to evaluate a chain of models or a chain of images, you can be doing inferencing on one while you're setting up the next. And this is what this is really designed to do, is basically create that asynchronous, almost swap chain-like behavior. So once you've bound the resource to the system, it's a really simple call. You'll ask the runtime itself to evaluate the model that you've seen. Once you call evaluate model, you'll be given back the resources, or given back the results. In the case of MNIST, what you'll be given back is basically a list of numbers and the probability that any one of those numbers was the result that you have. So you'll have to write a little bit of code to extract out the results. So if we look at my code here in PowerPoint, it really does this thing that it iterates itself through the return and finds the maximum value of what was returned from the system. So that maximum probability is the most likely number that sort of came back from the system. So all I've really done here in code is done, like I said, load the system up, load the data into the system, load the model into the system, bind the resources, and then call eval. So if we look here quickly, I will swap over to my laptop and show you what this looks like in practice. So this is a very simple application that basically has on top of it a graphics canvas that I can write against. And if I look here, you'll see me say number 3. And I'll click recognize, and it finds it as a 3. So what it's doing here is basically taking this image, taking the pixels, binding that to a D3D resource, providing that to the engine. The engine gets the results come back as that mapping of image to probability, or of number to probability. We choose the maximum probability, and that's what you have. So As I mentioned before, one of the things that's really important is that we've built the core platform technology, but we've also realized that one important part about it is that no platform technology is useful without the tools behind it. So as I mentioned earlier, we've built a number of converters that allow you to take a model and convert that from a number of different frameworks that are out there, Caffe, CNTK, TensorFlow, and bring that into the Windows ecosystem. We've also built the beginnings of integration into Visual Studio. In the Windows SDK, there's a tool called MLGen that, given any model that you've imported into an Onyx file, will generate all of the core class wrappers you need to basically do a core evaluation. And a lot of that code that I've seen here, it sort of does for you. There's a visualization tool called Netron, and most importantly, we have enabled picks for machine learning. So I'm sure a lot of you here are used to debugging with picks. What we've done is made it so all of the events that happen in the machine learning timeline are part of picks. So what we do in ML on the GPU is we use DX12 compute, and you will see machine learning events show up in the DX12 compute queue. So you'll see the beginnings of any one of the operations inside of the machine learning evaluation show up in the GPU timeline. And you can also see events that come up in the CPU timeline. And really what we're gonna try and enable is the ability for you to take a look at the evaluation timeline along with the rest of your game. So as you're doing those things together in that sort of demo I showed you, the ray tracing, you want to be able to see how much, and control how much is going where and how much resources I'm using and what is the timing of all the command lists and buffers that are happening, and really use the tool that you're used to using, picks, to do that. So like I said, today we've enabled picks. We're going to continue to invest in that to really enable debugging in the core of what you do today. So in general with that, I'll introduce Daniel.
Thanks, Stuart.
You're welcome.
Okay, I'm on, cool. So yes, Dan Kennett. I work in the Xbox Advanced Technology Group, and I'm going to talk to you about one of the projects that we've done internally at ATG today. Before I get into that, I wanted to gush just a little about how cool I think machine learning is. It's one of those things where, for me, it feels a lot like when I first got my hardware TNL card for the first time and moved out of fixed function. It feels, or at least went to hardware TNL, it feels like the first time I wrote a pixel shader. It feels that we're at a point with the hardware and the software that we're starting to do some really amazing things with machine learning. And I looked on the net for a couple of images that I've put up of different things that I saw at SIGGRAPH or papers that I've seen. I do want to call out that these are illustrative only, with the exception of Project Malmo at the bottom. I'm not making any claims about Windows ML and these projects, but they were really cool things that I've seen online where developers are starting to leverage machine learning in their games. There's lots of different places that we can use machine learning in our titles today. AI bots, a lot of people have been talking about that. We've seen some interesting Dota bots, we've seen some interesting StarCraft bots and other stuff in that space. There's a lot of interesting services that we can do, smart matchmaking. There's a lot of stuff around like abusive intent and inappropriate content detection that can be done. On the art and content side, some of the stuff like NVIDIA has shown with their up-resing of textures and images. The Remedy a couple of years ago showcased how they can take a voice clip and some training off facial animation and use new voice clips to generate new facial animations. And some stuff I think by Disney or Pixar was shown at SIGGRAPH doing something similar this year. There's been some interesting research into post effects and training autoencoders and different models to actually replicate things like depth of field, different lighting environments that are trained on one set of geometry and then applied to another. And for me, one of the cool things with Windows ML, because it runs on any of the different pieces of hardware and coupled with Onyx, really allows developers to start experimenting with lots of different technologies and pieces that are out there. Even within Microsoft, working with Microsoft Research and other groups, some groups are using CNTK, some groups are using Keras or other things, and Onyx has allowed us to work with them and share stuff back and forth. So one thing I wanted to talk about today was Unity ML agent support. So most of you probably heard about it at this conference or before. If not, my first bullet up there, I took straight from their GitHub. I can read it, but it's effectively what it says. It's a great plugin allowing you to do work within Unity on machine learning. And so what we've done in the ATG group is add Windows ML support into their system as just another type of brain that you'll select. And I'll quickly jump into what and how that is. So the way we made it work, one of the key things that we wanted to do in getting this enabled was not require you to change any of your code significantly or the training pipeline that Unity's already set up. So right now, you train as you do today. If you're familiar with using the technology, you use Onyx to convert the TensorFlow over into the Onyx model. At runtime, you select a new brain type, which is Windows ML. You point it to the Onyx graph, and then you pretty much just run. We tried to make it as simple and as straightforward as possible. In more detail, the way we went about doing this is we grabbed the latest public Windows Insider build, which had the preview of Windows ML in it. We grabbed the latest SDK that went with that at the time. We used the TensorFlow plugin, which, as Stuart called out, is now released onto the GitHub. We used that to convert the models over. We exposed the three main APIs, load, bind, eval, put that all together, and it was one of those moments in dev where it sort of just worked. You know, there was a few bugs, you get rid of those, you hit F5, and all of a sudden, all the demos are just up and running. So it's been a great experience for us in terms of testing out. I do have 2 demos, which I will show. So I'll switch over. So these are 2 of Unity's stock WinML demos. These are running on the 0.2 release. That's what we had at the time that I put this deck together. I haven't added any additional bits or pieces to this because I really wanted to show that we took the demos as they were, we added this new brain type, we changed the type, we did the conversion, and we ran. Everything that Unity's done continues to just work within their reinforcement layers. And then the other one is their crawler demo, and it's the same thing. Basically, we ran the converter, we changed the brain type, we recompiled, and we ran. One second, sorry about that. See if I get this right. Yes. So a couple of things to know. We're planning to release this later this year. We already have it mostly up and running on the 0.3 release from the Unity folks. This has also been a really great exercise for us internally to test out Windows ML and Onyx. You know, unit tests are great, but starting to use other people's code and other people's stuff has been excellent. Internally within ATG, we've also started a number of different incubation projects around this space. Again, for me, this has been really exciting because the ability to run in any silicon is starting to open up really interesting scenarios where I can potentially run my inference on an integrated GPU while still leaving the CPU and the discrete card to do everything that they do today. There's a lot of interesting techniques that we're starting to explore as more and more people that we're talking to are aware of ML. All these different opportunities are starting to open up. And hopefully next year we'll have a lot more demos to show you guys. I think I'm back to Stuart.
Awesome. Thank you, Dan. So in general, as Daniel pointed out, really one of the cornerstones of Windows ML is to make the core access to the technology simple, but give you access to all the underlying power of the hardware. So what you have is any DX12 class GPU, any neural network processor that can basically adhere itself to the DX spec will basically become part of anything that you can program to. And really what we're trying to do is make it so that all of the silicon that's possible in the machine really be usable by Windows machine learning, usable in your game, usable for the things that you want to do with it. So in general, you know, where we are today is that Windows machine learning right now is in its beginnings. So what we've done today is at Windows Developer Day, we announced the first preview of Windows Machine Learning. That preview was really driven by the computer vision style scenarios that I put up here, image recognition, handwriting recognition, lots of common things that we do in a game. So if you think about lots of fun things you can do is look on Mixer and identify a person, find their face, put a hat on it, right? All of those kinds of fun things are really driven by the core of computer vision. So we've built a lot of support in the platform for computer vision style scenarios. We've done a good bit of work on classical machine learnings, things that do classification to decide whether or not something, I don't know if you guys have seen, is it a hot dog or not, right? Like all those kinds of things. So in general, what we've really done is drive for a lot of the very core basics. Today, you can get access to it. It is publicly available for developers and insider builds. It will be broadly available, as I mentioned before, on all the different editions of Windows in upcoming releases. But really what we've done today is, like I said, pick it up, take a look at what's there. It is out there in the public. There is a lot more work that we're doing, and when you really look at that, that's kind of what we're here to do, is we know no matter what, we've only scratched the surface, and we know that you want more. What's coming next really soon is we're building what we call custom operators. Is when we think about the neural network system itself, the space is moving very fast. Every day, new techniques come up for skeletal tracking and reinforcement learning and bots and all different kinds of things. We don't want the platform itself to slow you down. So if you want to create your own custom work to basically enable your specific machine learning technology to work, you can. So things like you can write the CPU operator in regular CPU, but you can also, because we're used to writing shaders, you can write a shader, a DX12 shader, and have that become part of your machine learning network and part of the thing that analyzes the graph of data as it comes in. So you'll be able to do that in an upcoming release and really expand the system in any direction you want to take it. On top of that, part of the state-of-the-art of machine learning itself is really getting every single bit of let's call it, ability of the hardware itself. On top of that, some of the really complex systems are a lot of math and a lot of data. So there's a common technique called quantization, which really takes big floating point data and brings it down to smaller precision. We're also working heavily on lower precision math with the GPUs and systems that can take advantage of it. So things like we'll see this afternoon, like Tensor Core. When you really look at it today, I don't know if anyone here has gone out and looked at the DX12 shader compiler. We have already enabled shader model 6.2 to do FP16, so floating point or half floating point data. And we'll continue to push those technologies which are relevant to machine learning into the core of the DX engine. So all the things that we do in machine learning will be shared in graphics and you'll be able to get access to them. We're pushing a lot of that into that. As I mentioned earlier, other things like D3D textures. Today we do UAV, but we'll actually take a look at SRV and other types of texture support. We're doing a lot of work with the audio engine and other types of hardware, because if you really think about making something perform well, there is a lot of silicon that's available. There's a lot of input devices. So we have cameras and controllers and headsets and all different kinds of things that we want to draw data from. So if we really want to make a very highly interactive game that performs, we need to take data from all of those places and drive it through the engine. And those are things that we're really deeply invested in. And if you come to our next talk, you really see what we're doing from the hardware side and acceleration, because no matter what, like I said, machine learning workloads are very hungry, and making them run fast is something that we really want to take advantage of. So we've built the core of the engine to run everywhere, and we're doing a lot of work with our partners like NVIDIA to really drive very fast inference and a lot of performance in the hardware that we have. So in general, like I said, here's where we are now. We've released things. We're going to be doing a lot more. You'll hear me, say, if there's stuff that you want to see in the system, we really want to hear that from you. But in general, we know there's a lot of stuff coming up, and this is what we're working on. On top, there we go. So what's important is that there's a lot of resources that we're starting to put together. All the things that you're used to seeing in terms of tools and things for getting started. If you look at the DirectX blog, we're starting to get together all of the tools that you need to really get access to the system. Links to get started. The converters are up and online. We have a lot of tools. And we're going to be driving stuff into DirectX Tech. So if you're using that forum, we'll have a forum there for machine learning specifically so that you can interact with us, ask the questions that you want, and really get help with the things that you're trying to do with machine learning on the platform itself.